Welcome to this explainer. Today, we're taking a deep dive inside the thermal reactor to break down the exact anatomy of nuclear power. We're going to see exactly how this technology safely turns invisible atomic collisions into the massive amounts of electricity that literally power our modern world. Nuclear power can sometimes feel a bit like science fiction, But today, we're exploring the elegant, carefully balanced engineering that makes it all a reality.
So here's our roadmap for today. We'll be hitting Section 1, Basics of Thermal Reactors. Section 2, The Magic of Moderators. Section 3, Heavy Water versus Light Water. Section 4, Inside the Reactor Core. And finally, Section 5, Types of Reactor Designs. Let's get right into it.
But before we actually start building a reactor, I want you to consider this mystery from the source material. How in the world do you harness and control a blindingly powerful nuclear reaction using something as ordinary, as everyday as water? It honestly feels kind of counterintuitive when you think about the immense, violent energy of an atomic split. But as you'll see, water is the fundamental secret to the designs we're about to explore.
Section 1, Basics of Thermal Reactors. Let's lay down the absolute foundation of what makes these machines tick. Okay, so a thermal reactor fundamentally requires two specific ingredients to function. First, you need a fuel with low fissile enrichment. And second, you need a highly critical component called a moderator, which is used to slow down fast-moving neutrons. See, when uranium atoms split, they eject neutrons at just absolutely incredible speeds. If they're moving too fast, they actually won't trigger the next atomic split. They just sort of fly right past the target. So we desperately need a way to hit the brakes on these neutrons so the chain reaction can actually sustain itself. Section 2, the magic of moderators. This is where we figure out how to hit those brakes. To get that perfect Goldilocks speed, not too fast, not too slow, we have to look at the math. For maximum efficiency, a moderator really must balance three key factors. First up, a high-energy decrement. Basically, the neutron needs to lose a massive amount of its punch with every single bounce. Second, a high scattering cross-section. This just means neutrons have a really high probability of actually colliding with the moderator atoms in the first place. But this third rule, this is the deal breaker. You need a low absorption cross-section. If your moderator acts like a sponge and absorbs those neutrons instead of just bouncing them around, well, your chain reaction just dies right there. Right. So you calculate the slowing down power by multiplying those first two collision factors together. But the ultimate test of any material is what's called its moderating ratio, or MR. You simply divide the slowing down power by that pesky absorption cross-section. The higher this MR number is, the more efficiently your reactor is going to perform. It's a delicate balancing act for sure. Section 3, Heavy Water versus Light Water. Let's see how different materials stack up in the real world. This brilliantly illustrates the core engineering trade-off we're dealing with. Light water, which is literally just standard H2O, slows neutrons down really efficiently, but it unfortunately absorbs way too many of them, leaving it with a moderating ratio of only about 70. To make up for all those lost neutrons, you're forced to use fuel that is enriched to roughly 3%. Now, heavy water, or D2O, on the other hand, it has a massive moderating ratio of 12,000. No way, right? Because the deuterium in heavy water absorbs almost zero neutrons, this insanely high MR allows the reactor to run purely on natural unenriched uranium. It's a huge operational advantage. Section 4, Inside the Reactor Core. Let's move from the physics to the actual physical machine. All right, here is the heart of the whole operation. What you're looking at is a massive steel pressure vessel. This is the absolute fortress tasked with safely containing the immense thermal energy we are about to unleash. Let's break down what's inside. Notice the fuel rods? They're tightly encased in these zirconium clads, and they are completely surrounded by whatever moderator material we've chosen. Now, look at the movable boron or cadmium control rods. These are absolutely crucial. They are your gas pedal and your brakes. Pull them out, the reaction speeds up. Drop them in, they absorb the neutrons and shut the whole reaction down safely. And finally, check out the coolant piping loops. That coolant flows rapidly over the hot fuel rods to constantly carry all that intense heat away. Section 5, Types of Reactor Designs. The crucial point here is how we actually manage and extract that heat. So, designs really diverge based on pressure. For example, India heavily utilizes pressurized heavy water reactors, or PHWRs, kind of like the famous Canadian Canada model. In these, the coolant is kept under extremely high pressure so that it literally cannot boil, even at insanely high temperatures. This sits alongside light water reactors, which give you a couple of options. They can either be pressurized to prevent boiling, just like the can do, or they can be deliberately designed as boiling water reactors to let the water turn into steam directly inside the core itself. But honestly, regardless of the specific water or design used, the ultimate process follows this exact linear progression. The coolant extracts fission heat from the core, it uses that heat to generate steam, and that steam turns a turbine to produce our electricity. It is truly elegant. I mean, think about it. All of that incredibly complex quantum physics, the careful balancing of mathematical cross-sections, it all ultimately serves to just boil water to spin a giant fan. Actually, scratch that. It's a massive, highly engineered turbine, not a fan, but you get the idea. It's brilliant. And of course, to ensure maximum safety, this entire complex system is shielded and housed in a containment building that is deliberately maintained at subatmospheric pressure. This is such a smart design choice to prevent outward leaks. Because the pressure inside the building is lower than the outside world, if a breach ever did miraculously occur, the outside air would instinctively rush in, keeping any dangerous material securely trapped inside the facility. So from microscopic atomic collisions to massive steam turbines, the thermal reactor really is a marvel of delicate, precise balance. We'll leave you with this final thought to chew on. Knowing the intense, meticulous engineering required to safely harness this power today, how will these brilliant designs evolve to meet tomorrow's skyrocketing energy needs? Thank you so much for joining us for this explainer. Hopefully, you now look at nuclear power not as some kind of dark magic, but as a masterpiece of carefully managed science. Stay curious, and we will see you in the next one.